Yo, 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 what's up, McHugh crew? Today we're talking about collisions, explosions, and conservation of momentum. Yeah, I can't keep that energy up. Been watching my kids watch YouTube, so I tried to do a thing. Anyways, can't stress enough how important conservation of momentum is to classical physics, and actually all of physics. But basically, if we're talking about the sort of things we've been talking about so far, conservation of momentum and conservation of energy are twin pillars that everything else is built up on. I'll talk about how conservation of momentum basically, like, you can get Newton's laws of motion out of conservation of momentum later in this video. Anyways, click like and subscribe for updates. Anyways, collision's easy. You know what a collision is. Collision's when two objects hit into each other. Now, really, what we want to talk about is there's two basic types of collisions that we can have. What we call a perfectly elastic collision, where two objects hit and bounce off of each other. So since I have not anything better, so our kinematics tracks at school would be great for this. It's actually what they're designed for. But an elastic collision between two things that are going to be, that are going to bounce off of each other, like these two quarters, it's an elastic collision. We'll talk about how that relates to conservation of momentum in a little bit. For a perfectly inelastic collision, that would be two things that come together and stick. So if I had one of these and then like a chunk of gum and I put it into the gum, that would be a perfectly inelastic collision. So really perfectly elastic, perfectly inelastic, they're really two ends of a spectrum. And in between there, you're going to have partially elastic, partially inelastic equation or formula collisions. So in real life, perfectly elastic, perfectly doesn't exist. Most things that we would consider perfectly elastic are going to be like right here, where they're almost perfectly elastic. And the same thing with perfectly inelastic. They're going to be almost perfectly inelastic, but not quite, because we're gonna just not have the energy transferring exactly the way we want it to. So if we're talking about something that's perfectly elastic, things that we could imagine or at least approximate to be perfectly elastic would be like pool balls, right? When you hit the cue ball into one of the object balls, cue ball stops if you hit it dead on, and then the object ball basically keeps going. That's a perfectly elastic collision. If I bounce a ball off the ground, that's a perfectly elastic collision. A perfectly inelastic collision would be me trying to like bounce dough off the ground. It's just not going to work. Anyways, with perfectly elastic collisions, the total kinetic energy before and after a collision is the same. So if we think about what happens in a real collision, if I bounce a ball off a table, well, it's going to convert some of that energy into heat, right? The ball bounces up, yeah? If you go and you take a racquetball and you knock it around the court a couple times, you can feel the racquetball warm up. Or, if you're bouncing a basketball, it'll warm up after a little bit of time. Now, it's not going to warm up like really, really hot, right? Like, I can't make tea by bouncing a ball a ton of times and then sticking it in my, well, I wouldn't want to do that anyway. It'd make me make my tea racquetball flavored. Anyways, not that I drink tea anyways. So other things that's going to happen in a collision, they make sounds, right? So if we had a perfectly elastic collision and we dropped a ball from 1 meter, it's going to bounce, hit the ground, and then it's going to rise back up to a height of exactly 1 meter. But it would do this and it wouldn't transfer any of its energy into sound or heat or anything like that. You would just have this ball bouncing straight up and down at the same place silently forever. It'd be really, really weird. When we talk about real collisions convert that kinetic energy into heat, sound, and, kinetic energy for the floor, because the floor is going to shake a little bit. Like, there's other places where that energy is going to go. There's other transformations for that energy. So if we have a perfectly inelastic collision, total kinetic energy is reduced to whatever the minimum possible value is. We need to use conservation of momentum to figure out what that velocity is, but perfectly inelastic collisions, we're going to lose kinetic energy, and kinetic energy is not going to be conserved. Once again, that's not saying energy is not conserved, that's saying kinetic energy is not going to be conserved. An explosion is anytime some force pushes two objects apart. So two things work together, the force pushes them apart. So physicists would say, well, actually everyone would say, hey, if I have a bomb, that's me trying to draw a bomb, and it explodes into two parts, we would go, oh, hey, that's an explosion. Physicists, on the other hand, would go, oh, hey, if I've got a quarterback holding a football, and then the quarterback exerts a force on the ball and throws it, ooh, geez, the quarterback and ball exploded. That's a weird thing physicists do. But literally in Giancoli, you've got a picture of a kid like punching a box in a boat. And it's the same idea. We're using that to go, hey, it's an explosion. So, but no one would really say like, oh my goodness, the quarterback exploded. Be crazy times, some Last Boy Scout stuff. Anyways, conservation of momentum. Total momentum of a system is constant before and after any interactions. So basically, if we add up the total momentum, so P total, so TOT is what I use for total, and then the naught is going to be initial, and then this total here, so POT total initial is equal to POT total final. So TOT is going to be total for both. The F is going to be final. And there we go. Now, with conservation of momentum, the system's center of mass moves in a straight line as long as there's no external forces acting on the system. Any external force would act like an external force, would basically make the center of mass accelerate like it was Newton's second law. So pulling out one of my old textbooks here, I've got a favorite problem of mine. So basically it's an old Charlie Brown cartoon, and in the cartoon you see Snoopy walking back and forth on this boat, and as Snoopy walks one way, the boat shifts the other way. That's what's going to happen in real life. If you're walking on a canoe, it's your center of mass plus the canoe's center of mass together would be the center of mass of the system. That center of mass is going to stay constant, and as you walk forward, you're going to push the canoe backwards. And we can think about this in terms of conservation of momentum and Newton's third law. If you really want to, you probably should. There's going to be a test. Anyways, so real quick, Newton's laws and conservation of momentum. So objects in motion remain in motion. That's Newton's first law, right? Conservation of momentum, basically, if there's no interaction, so no collision, no explosion, the P's of both objects, the momentums of both objects, or all the objects in the system, is the same. Okay. Well, what about Newton's second law, FMA? Well, Newton's second law, FMA, really comes from, so if we start out with delta P is equal to F delta T, yeah, which we said in the last video. Well, delta P is really M delta V. Mass is going to remain constant, right? So M delta V is going to be F delta T again. Well, if we solve this for F, we get a delta T over here, and that's equal to F. And the astute among you will notice that that is an A, and we just turned delta P is equal to F delta T into FMA. So once again, you know, this conservation of momentum stuff just basically goes straight into Newton's laws. And then for Newton's third law, for every action there's an equal and opposite reaction. Well, when an object interacts either through a collision or an explosion with another, it will basically exchange an impulse, right? So impulse is a change of momentum. Well, that change of momentum, if to keep the total momentum of the system constant, if one object gains momentum, the other was going to lose momentum. That means one's going to have a force exerted on it in the positive direction, the other one's going to have it exerted in the negative direction, and the time is going to be constant for both of those, because, you know, I can't push on something for longer than it pushes back on me. It just doesn't work that way. So Newton's third law basically, or all of Newton's laws come right out of conservation of momentum. So, and then I am out of order, and I'm 12 minutes in, so I'm not gonna, okay. If I've got a system of two objects, so basically for those two objects, I can write P total, the total momentum, is PA plus PB. Or I can write it in terms of mass and velocity as MA VA plus MB VB. Okay? Now, I've got three different types of interactions: elastic, inelastic, explosions. So right now I've got these two just drawn out in vectors. So whatever the length of these arrows is combined, after they collide, I'd have to be able to add up the same vectors. So for a perfectly elastic collision, before the collision, so if I have an object at rest being hit by an object that's moving, and then it transfers all that momentum here, I can write that in terms, well, okay, so basically when I write this, every object is going to get its own momentum term, because every object is going to have momentum. So this would be PA naught would be here, PB naught would be this here, PAF would be here, and PBF would be there. Now, if the masses of both objects are the same, then I can basically come through and cancel out the masses. If this is at rest before and this is at rest after, whatever the velocity of this is going to be the velocity of that. So if I had a frictionless piece of paper and I slid my coin this way, then the other one would hit and move at the same rate. So now, what I can also say is that the total kinetic energy has to be the same, but this is only if it's a perfectly elastic collision. So the initial kinetic energy of A plus the initial kinetic energy of B has to be equal to the two final kinetic energies added up together. for perfectly inelastic collisions, we can think about the same thing, but inelastic collisions are sticky collisions. So if one's moving before and one's moving after, or one's at rest, afterwards, they're both going to be moving, right? They come together and they stick together. So this would be like, you know, two train cars coupling together is an example of an inelastic collision. So we're going to have one term for each object. So PA naught, PB naught, and then we just have one over here because it's P total F. When we go and we write that out into our mass and velocity, we'd get MA VA naught plus MB VB naught. So just a little note here, I don't have knots on the A or the B here for the mass because the mass is constant for right now at least. Now here's what's going to happen over here. Actually, I want to write it down here. So MA VA naught, MB VB naught. Well, what's M total going to be? M total is going to be MA plus MB. And then that whole thing is going to get multiplied by, oh no, that's not purple. There's purple. By V total F. Okie dokes. So whatever the mass of these two combined is, it's going to be the same as this. So if I just give these masses, say they're equal mass, whatever this velocity is here, it's going to be half as much after they stick together. Okay? Now, we've got one last one, and that's explosions. So for explosions, it's going to work the same way. So M total is going to be the total mass of the bomb, and then it breaks up into two different masses heading different directions. So P total is going to be PA final plus PB final. So, I should have a, so, and then the masses here are just going to be MAV. And if you look at this, this is the exact opposite of what we have here, right? So P total is really going to be, or P total initial would be MA plus MB V total initial here. So I am recording a video. Please don't make a thing of it just on the off chance that somebody's still watching 18 minutes in. Now, we can extend this to systems of more objects, right? So 2 objects is going to be like the minimum that we'd want to do. But if we've got an elastic collision with multiple objects, we would just add an extra term for each one. So PAF, PBF, PC, all the way up to PN. For inelastic, no, here's the thing. We're not going to normally have a large number of things colliding together at the exact same time inelastically, but we would just have P total F as just one term at the end when everything's clumped together. For an explosion, we'd get P total naught, because everything's initially in the same place, will be PAF, PBF, PCF, blah, 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 PNF. So if we're talking about a real like bomb or firecracker exploding, it's going to explode into more than 2 pieces, right? And we could figure out where like the momentum of all the pieces based on, you know, their mass and their velocity, and we would find they would all add up to 0 if it wasn't moving initially. If it was moving, then it would be whatever the initial momentum is. Now, yeah, okay, so that's basically where we're at. If we want to get a little bit further into like how much people, physicists, really believe in conservation of momentum. So back in like the 1920s, 1930s, There was, well, there still is, but people were studying nuclear decays. So beta decay is when we have a neutron in the nucleus that converts into a proton plus an electron. So this does not violate charge conservation because we have 0 charge here, +1, -1. Charge conservation is fine. What we would find later on is lepton number is not conserved. But you don't know that because you don't know what a lepton is. But here was the thing. So they knew that before they had a neutron, and then afterwards they had a proton. Now, the mass of a proton is something like 1,831 times the mass of an electron. And don't quote me on it if it's like 32, like don't at me in the comments. I love reading your guys' comments, by the way. It's been really informative. But this is gonna have a momentum going one way. So I'm just gonna write that as PP. And then there's gonna be an electron that's gonna have a momentum going the other way. So people were like, oh, hey, we should measure what this is. And what they found was, so basically, if you know how fast this is coming out, you can use it to calculate the recoil of the nucleus and figure out stuff about the nucleus. But these electrons didn't all come out at the same speed. So a guy by the name of Wolfgang Pauli was like, you know what, we can't violate conservation of momentum. There has to be something else coming out there. So what he came up with was a new particle. So he said neutrinos are also created. Now, here's the thing. Back then, they could add bubble chambers and cloud chambers. They could detect anything with a charge. And they weren't detecting anything else coming out. So these had to be neutral. And they had to be very low mass. So much, much lower mass than an electron. Possibly 0 mass. So for a long, long time, there was a discussion about whether or not neutrinos had mass. And that has literally been like, when I went to high school, they were like, oh, no mass. Anyways. And then the other thing is they could only interact through, so we've got our 4 forces, right? Gravity, and since they have possibly no mass, they wouldn't interact through gravity. Since they have no charge, they're not going to interact through electromagnetism. So they only interact through the weak force. So basically, Pauli comes up with this, and he writes a paper on it, and then he's kind of like, you know what, I did a really dumb thing. I hypothesized a particle that no one would ever be able to detect. So, you know, that was dumb. I should have just kept my mouth shut. In the 1950s, I think it was like 1958, 2 guys by the name of Clyde Rains and Cowan and Rains actually built a detector that detects neutrinos. Some of the most interesting detectors in the world nowadays are neutrino detectors. So they're these huge tanks full of, usually it's heavy water with, so heavy water, instead of having H2O, hydrogen and oxygen, it is not regular hydrogen, it's deuterium. It's hydrogen with an extra neutron in there. And these tanks are thousands and thousands of gallons, and they're lined with photomultiplier tubes. And they're looking for basically little tiny flashes for when a neutrino does actually interact through the weak force. So right now, there's billions and billions of neutrinos streaming through every square centimeter my paper here every second from the sun. So the sun creates them, and even though it's nighttime when I'm videotaping this, there's still going to be neutrinos streaming right up through the earth through my paper, which is, you know, nuts. And how do we know about them? Well, we wouldn't have known about them because no one would have ever looked for them if it wasn't for Wolfgang Pauli and saying, oh, hey, momentum has to be conserved. So once again, click subscribe. One of my subscribers will win this cutting of the classroom pet. Put it in your dorm room and convince people of that gender that you like that, hey, you can keep stuff alive. It'll really impress them. Okay, be safe, people.